I am thankful to Dr. Mustafa Misbah, working at Electrical and Computer Engineering Department in Sultan Qaboos University as Associate Professor, for providing the PowerPoint slides for these lectures. I have slightly modified the original slides. Again, thank you very much, Dr. Mustafa Misbah. Assalamu alaikum wa rahmatullahi wa barakatuhu. Alhamdulillahi Rabbil Alameen wa salatu wa salama ala ashrafil anbiya wal mursaleen. Amma ba'd. In the previous part of the lecture, in two examples, you may have observed that to determine the stability of a linear dynamic system, we need to find out the poles of the systems. And poles of the systems fundamentally are the zeros of the characteristics polynomial. And you may have noticed that whenever the degree of the denominator polynomial is increasing, it becomes cumbersome to compute the zeros of the polynomial. Therefore, in 1876, an English mathematician, Edward John Routh, suggested the arrangement of the characteristic polynomial coefficients to determine the number of poles on the right half plane and on the imaginary axis. So this method gives us information of the number of poles in the right half as plane without actually finding the poles. So the method is very efficient and it is simple. The same technique originally was independently developed by a German mathematician, Routh-Hurwitz, in 1895, and since 1905 this method is known as Routh-Hurwitz criterion. So in this part of lecture, with the help of a fourth order polynomial, we will show how to arrange the coefficients of the polynomial to determine the stability of the system. So the first thing, if we are looking to this transfer function, we have the denominator transfer function. So we start with the first coefficient in the first row, then we will leave the second coefficient and we take the third, and then we take the fourth. Then with the odd coefficient we will start, and just you can see here that what will happen. Here if we see the A4 is, we write here, then we write A2 here, we leave A3 as it is, then we write the A0 over here. Similarly, here we see A3, this is S cube, and here is A1, and then because after A0 there is no coefficient, this is 0. So then we will find the rest of the coefficients in the table, and the procedure is as follow. So on this slide we will show the arrangements of the coefficients, that how the system and the polynomial coefficients are arranged to determine whether the how many number of poles are in the right half S plane. So initially from the previous page we copied these coefficients in the same way. So here we see now how to arrange them. We will take these two elements over here, Like these two elements we copy here, and then these two elements we copy here, and we will divide this by A3. So then calculating this determinant divided by A3, this gives us another coefficient to what we are saying, B1 coefficient. Similarly, we calculate the second element of the row. In the second element, just note that this column is the same as the previous determinant, only this column is changing, and this is this column. From here we copy the column and we put it over here. A3 here and here is same, and if you do this calculation like A4 multiplied by 0 minus A0 A3 whole divided by A3, so just do this computation, you will see that here you will get A0. Do this calculation by yourself and see whether you are going to get over here A0. So B2 will be equal to A0. Similarly, we go for the third one. Here if you see both of them are 0. Here these two elements are 0. This is why we get over here 0 again. Note here in the denominator for all of the elements in row number 3 in the denominator are A3. This green color here, here and here, they are the same elements. Now we look for the next one. So here when we come, we will take these two elements A3 and B1, and then we bring this column A1 and B2. Here of course we know that B2 is A0 and this is B1. In this row, for all of the elements in the row, in the denominator we will have to write B1. So it will become like this. So here we have 0 now, and similarly the other element, and because here are zeros, just note one thing, for all of them this column, this column, this column is same. The denominator for all of the element in one row are the same. Here again note that this column, this column, this column is same, only the second column is changing. The denominator in one row is fixed. Similarly in the third row again they are fixed. Now here when we will write, just think what will happen. It is easy. Here we will take B1, C1 and B2 0, and in the denominator C1 will come, and in all the elements the first column will remain same. So let's see what is happening. Here if you see the similar thing, here if you do a little calculation, just check here after calculation at the end you will get A0. Just try it whether you can get A0 here. Then we move for the next element. So here because this and this is 0, here you will get 0, and similarly here again you are getting 0. Now the table is completed. How we can determine the system, how many number of poles are in the right half S-plane? We see that how many times the sign of the coefficient in the first column are changed. Like here in the first column we have elements A4, A3, B1, C1 and D1. If A4, A3, B1, C1 and D1 have the same sign, this means there is no pole in the right half S-plane. But if there is a sign change over here, like suppose A4 is positive and A3 is negative, so there is one sign change. And suppose then B1 is negative, C1 is negative and D1 is negative, this means that only once in the column the sign has been changed, This means there is one pole in the right half S plane. If here it was positive, then here it is negative, then again it becomes positive, and after that everything remains positive. What is the meaning of this? The sign change from plus to minus and then from minus to plus. This means the sign has been changed twice. Therefore, there are two poles in the right half S plane. So the number of poles in the right half S plane are equal to the number of sign changes in the first element of the Routh-Hurwitz table. So the table will look like this, and you have to see the sign change, number of sign changes in column number 1. So if you see the number of sign changes are 2, this means there will be 2 poles in the right half S plane. If you see there is no sign change in the first column, this means the system is stable, that there is no pole in the right half S plane. It is possible the system can be marginally stable in this case. If there are 4 sign changes, this means 4 poles are in the right half S plane. If there are 3 number of sign changes, this means that 3 poles are in the right half S plane and 1 pole in the left half S plane. If there are 2 sign changes, so in this particular example, there will be 2 poles in the right half S plane and 2 poles will be in the left half S plane. So here we will discuss an example. In this example, the open loop transfer function is this one. Suppose this open loop transfer function is g of s. Then the closed loop transfer function from here to here, this will be t of s is equal to g of s divided by 1 plus g of s, as you have studied this in chapter 5. So then the closed loop transfer function will look like this transfer function, and here now we want to determine the number of poles in the right half S plane. So on the previous slide we find the transfer function of the system is this one. So from this transfer function we generate the Routh-Hurwitz table. So here we see s cube, then s square, then s, and here s to the power 0. Then we start to write down the coefficient 1. We write this one, leave this one, and we write the other one, 31. Then we leave this one, and after this definitely nothing is there, so that will be 0. In the same way we can write like this. Here we should note, like, the first row is divisible by 10. To simplify the calculations, it is better to divide both of these elements by 10. So here it will be 1, and then here we cut this and it will be 103. So the system will somehow look like this now. So these are the coefficients we will be treating: 1, 1, 31, 103, and 0, 0. As we discussed previously, like here we can very directly write that here it will become 0, but let's see that how to calculate the things. So here we write these two elements over here and these two elements at this place. In the division we will have 1, so when we calculate this will be minus 72, and here we will get 0 when we do our calculation because these two are 0. Let's see. So here if we are looking, these two elements are 0, so we got over here 0. But if these column like these two elements are 0, so we should know that here it will become directly 0. Now here the matrix will be 1, minus 32, 103 and 0, and minus we will be taking. So this 103 number, when we do all the calculation, it will appear over here. So let's see that what is happening. Here if we see, like here I have to write 1, 1 minus 72 in the first column, then 103 and 0 over here, and we will divide it by this element. So here it is 103. If you look to this table, this element is positive, this one is also positive, this is negative, so there is one sign change, and when I look over here there is another sign change, so there are two sign changes. This means there are two poles in the right half S-plane. Because this is a cubic polynomial, so one pole is in the left half S-plane. So here we will discuss the summary of the example. As we discussed before, the number of sign changes is equal to the number of poles on the right half S-plane. So here we see that this is plus, this is plus, this one is minus, then this is plus, so there are two sign changes. This means two poles are in the right half S-plane. The terminology unstable poles we say, but the right terminology is that two poles are in the right half complex plane or right half S-plane. So here if we see, it is plus, then it become minus, and then it become plus. So this is a plus to minus, like here it become plus to minus and minus to plus. This is why we are saying that there are two sign changes. So if we use MATLAB and to find out the roots, so here we are seeing that one of the pole is in the left half S-plane and two poles, because this sigma is positive, so two poles, complex poles, are in the right half S-plane. So the closed loop is unstable. And it is interesting, you should have noted this, the original system was stable system, but when we took the feedback and the system become unstable. This is why whenever we are going to design a feedback loop, we have to be very much careful that if the loop can become unstable. So this fact we will be using in the design. Thank you very much.